Okay, so I would like to start by thanking the organizers for the invitation and letting me to speak here. It's a privilege to be the first one to open the conference and the workshop. I'm sure it will be a successful and inspiring one. So let me start my talk, which is about some recent work on quantum quenches in the sine-Gordon model. And the method, somehow I want to put emphasis on the method which we used. This is a sort of a semiclassical approach, which I really like because it's kind of intuitive and transparent. It's an approximation, but I think it has a great potential to develop it further. And the work was done in collaboration with Gergely Zarán in Budapest. Okay, so the big context of the whole workshop, I guess, and as well as my talk is the out of equilibrium dynamics of closed quantum systems. Of course, there are many out of equilibrium situations in physics, but probably the simplest ones. The simplest one is that of the quantum quenches, when we somehow take the system out of equilibrium and then leave it alone and see what's going to happen. There have been many works on the questions regarding the asymptotic steady state after a long time. The obvious question is whether a system thermalizes after such a quench, or what is the asymptotic steady state. And I think it's fair to say that there are still some unanswered questions or unsettled issues. Just an example, in integrable systems we know that the asymptotic steady state is, generally speaking, is not a thermal state in any sense. But probably a GG, a generalized Gibbs ensemble, but it's still a bit controversial. For example, in continuum systems, these two works I cited here, it's not completely clear how to understand this, how the GG is defined, and there are other issues in the XXZ spin chain, which perhaps it has been resolved now, but it's quite interesting. But my talk is, in my talk, I want to focus on something else, the actual time evolution, the approach to the steady state, because much less known about this. And the obvious reason is that it's hard to say anything about this. Numerical studies are naturally constrained to sometimes to small systems or short times. And of course, we can try to do some analytics, and there were successful attempts in systems that can be mapped to free bosons or free fermions, like Luttinger liquid or the Ising spin chain. Okay, and then one might think that we are better off in integrable systems where at least we know something, we know the spectrum usually, but it's still very, very hard to say, to do any analytical calculation. We need matrix elements of operators, form factors, we need overlaps between the initial state and the eigenstates of the system, and these are not really known except a few cases. A promising direction is this something called the quench action approach, suggested by Jean-Sébastien and Fabian. And I won't have time to talk about this, but what I want to say is that my main reference for this talk is this paper by Bertini et al., who used both, so they studied quenches in the sine-Gordon model, and they used both these integrable techniques, form factors, S-matrix, overlaps, and so on, and this quench action idea to somehow somehow to be able to say something about the steady state, and somehow mixing these two two things. I think this is the cutting edge calculation now, really relying on the integrability of a model. And it's a very long, very nice paper, very technical. And what I will try to show you here is that we can reproduce these results in a much simpler way, basically. So let me quickly introduce the sine-Gordon model, which is a one-dimensional field theory. So phi is a bosonic field, and the interaction term is this cosine potential. So lambda is just a mass scale, but beta is the real coupling constant, and we are focusing on this regime when the system is gapped, and the spectrum can be understood in terms of solitons and anti-solitons, the scattering states of these particles. So what are these solitons? In a classical field theory, they just interpolate between minima of this potential, right? So this cosine has minima at these points, and the soliton interpolates between these neighboring minima. So it goes from 0 to 2 pi over beta, let's say. And anti-soliton is going the other way. Okay, so this picture was stolen from Giuseppe's book without his permission, but I hope it's it's fine. Yeah, we talk about it later. Okay, and if beta is smaller than 1 over square root of 2, then we also have bound states of these kinks called breathers. So the spectrum is a bit more complicated. So let me focus on this situation. If beta is larger than 1, then this is an irrelevant perturbation, and the system is gapless. Okay. So I want to study quenches in this system, and the quench I define by writing down the initial state, which has this very peculiar structure. Sometimes this is called an integrable initial state, because it resembles the integrable boundary states in relativistic field theories, integrable field theories. But physically, what it tells us that the initial state is a superposition of pairs of kinks, so pairs of solitons and anti-solitons. There is an amplitude k given by this k function, and this exponential structure tells us that these pairs of kinks are independent from each other. Okay, and so there is only one function that basically describes the initial state instead of infinitely many infinitely many. Okay, and this is a natural initial state for small quenches at least, because you can think of a let's say a local quench by creating some disturbance at some point, and then you create a bump in the field phi, and then what will happen is probably this bump will, so a soliton and an anti-soliton will form, and these kinks will travel apart from each other, and due to momentum conservation and the conservation of all higher charges, they will travel with opposite momenta. Okay. But this structure of initial states has been observed in many other systems, also free systems like free boson or Ising chain, but also interacting systems like the Lieb-Liniger model of 1D Boson gas or the XXZ spin chain. We know where there are exact solutions for an actual quench for the initial state. The initial state looks like this in terms of the new Hamiltonian, which governs the time evolution.
You take this as, I mean, it's your hypothesis of initial state.
Yes, and I should have put some references here that recently there have been very interesting results, and I think Gábor Takács will talk about it in his talk, whether this assumption is correct or not, I mean,
you can always engineer a state.
Yes, I can put it, but what I want to say is that yes,
translational invariant, then you don't know.
Yeah, of course. Yeah. So in many cases when we start the system from the ground state of translation invariant Hamiltonian, and we do a global quench. Not always, but in many cases, this is what we sort of find. I think that's fair to say. So I just want to defend this choice of initial state, but of course I could just write it down.
The most general, this is the point.
It's not the most general, yes.
It's a nice state.
This is a nice state, yes. And also in the paper by Bertini and Fabian and Dirk, they chose this state. So, okay. So let me review this paper, the results. So they looked at small quenches, and that will be important in a minute. So by small, they meant that the density of excitations, these kink pairs, is low. So this A and B indices, I'm sorry I didn't say that, but these can take two values plus or minus, let's say, so soliton or anti-soliton. Okay, so the density of, let's say, soliton anti-soliton pairs is given by this integral, and this is much smaller than 1. Okay. And they focused on 1-point functions, on the time evolution of expectation values. So they looked at this, these vertex operators, like this one, e to I beta half phi, which is a very natural operator in this model. Also for, in the applications of the model in 1D systems through in the context of bosonization. These operators are really natural. So they found, actually this is more or less rigorous, I guess, that this operator decays to 0 in this exponential way. And the decay rate tau is given by this expression. Okay? And they also looked at more general operators, e to I alpha phi, and but they could not derive such a result. They could basically give a short time expansion, and it has this form. Okay. So now here you can think that maybe this wants to be an exponential in the end. But of course, for this we need to know at least the next term in this expansion. So in that case, the decay rate would be different, something like this combination, right? But so in that paper they could not tell anything about this. And now what I want to do is to rederive these results within this semi-classical intuitive approach. And doing this, we will understand the real input behind these calculations, and also we will be able to extend these results. Okay, so the semi-classical approach was pioneered by Subir Sachdev back in the 90s. He was interested in dynamic correlation functions at finite temperature. And later the method was used also in the O3 nonlinear sigma model, in the Q-state POTS model. And then other people later started to use the model for quenches. In these papers, the Ising spin chain was investigated in a finite volume, and the quenches in that system. And in this paper by Stefano Evangelisti, the O3 sigma model was studied, quenches in the sigma model. So let me introduce this model real quick. So the idea is that if these excitations have low density, then these pairs of kinks will follow classical trajectories, more or less. So just let me say this, that as you remember the paper by Esther Schuricht and Bertini, they looked at really small quenches, so low density. That was their main assumption. And this is exactly the regime where the semi-classical approach works. So this is the reason why we will be able to reproduce their results. Okay. So the idea is that the particles, quasi-particles in general, here they are kinks, solitons and anti-solitons. They follow straight lines, but of course in 1D they cannot avoid collisions they will meet, and when they collide, we need some quantum mechanics. And what we can say is that let's put the super universal low energy S matrix at each collision. Because of the low density, only two particle collision. We only deal with two particle collisions, and this low energy S matrix is -1 times a total reflection. So if you take,
I didn't get it actually. What I mean is, what you are doing is low energy, but not low density. Because the system is integrable, anyway will give a straight line. And then the only thing we are using is the S matrix of -1, which is really zero energy limit.
yes.
So,
Yes,
when you
so-
say it's low density, it's low energy.
So I think so for small quench, and maybe we also need the quench to be slow, so we don't want to create very energetic quasi-particles. But it's very important, I think, that the density is low, because otherwise you cannot really say that these particles, this classical picture somehow breaks down, I think, when the wave functions, let's say, overlap.
Increase the density also. If you increase the density,
But
you
not
also
the
an high energy density, no?
Not an integrable case. Probably in 5/4 you're right.
Yes, okay.
The two things overlapping, the two concepts. But if you start with integrable model to start with, I think it's just low energy, but not low density.
Okay, but I think, okay, so first, the method is, I haven't said that yet, but the method is, doesn't rely on integrability in general. Now I'm using it for sine-Gordon. The other thing is that, okay, maybe we should talk about this later, but so in these statements in the integrable field theories are about asymptotic states, I think. So, I mean, what I mean is that many particles come in, they do something, and they go out, and then particle number is conserved in this sense, that asymptotically. But what happens in between?
Then you need low energy. Essentially, you don't want
Yeah,
to
low
reach
energy.
any
Yes,
threshold.
yes.
Is the
Okay.
point. You don't want to reach any threshold, so that the number of particles is reasonable conserved anyway, either integrable or not integrable.
Yes.
But is low energy once again.
And also low energy. Yes, also low energy. Both. So the idea, yes. Also, the original idea was this: that at low temperature, in this original works, both the density and the velocity, average velocity of these quasi-particles is both are low, and this is why, I mean, this is the crudest first approximation to put this S matrix. Okay, and then the idea is that the quantum mechanical expectation values are computed by averaging over these semi-classical configurations in a classical way, basically. So we have what is the configuration? The positions, initial positions of these pairs, the velocities of these pairs. Okay, so time runs in this direction, so velocity is obviously the slope of these lines, and the velocities are drawn from a velocity distribution. So the quench enters only through this velocity distribution, which is related to this amplitude in the initial state. Okay, but in practice, you give me a f of v, and then we can calculate something. In a thermal case, this is the thermal velocity distribution. Okay, and then also there are the charges, topological charges of these kings, whether they are solitons or anti-solitons. Okay. Now, so this, what I said so far is true probably in all applications of this method, but specifically in the sine-Gordon model, the particles are kinks, and so they are domain walls, as I showed you earlier, separating domains of constant values of the field. So phi takes a constant value, 2 pi over beta times an integer number, almost everywhere, except when a soliton or anti-soliton passes, when it increases or decreases by 1 unit, by 2 pi over beta, the value of the field. Okay. Now it's a very important observation that due to this very special S matrix, the sequence of kinks or domains is unchanged in time. So if you draw a horizontal line here, the order of domains is the same as at time 0. So you can feel that it's really a rigid, it has a very rigid structure, it's a bit too constrained, you can say, but let's see how far we can get with this picture. Okay, in this picture, I assume that there are only soliton and anti-soliton pairs in the initial state, and the initial state had phi 0, you see. So there are two kinds of domains, basically, the plus domain when we have phi 2 pi over beta, and the minus domain when phi is minus 2 pi over beta. And no other kinds of domains will be generated in the course of the time evolution because of this very restrictive S matrix. Okay? And now let me show you very quickly how to compute this expectation value in this method. So the idea is that I have to just count how many domains I shift when I walk along this dashed line up to time t to the right or to the left, because we know that this, again, the sequence of domains is conserved, so I just have to count where I end up, in which domain I end up by the time I get to time t. Okay, so this number is given by the number of kinks intersecting this dashed segment from the right or from the left. Okay, because if a soliton comes from the right, then I jump one domain to the right, and if it comes from the left, then I jump one domain to the left. Okay? Now, if this number is even, then we can just go back at time 0 and see in which domain we ended up. If this is even, then of course we again find ourselves in domain 0. So then the contribution will be just 1 to this expectation value. The normalization is the vacuum expectation value. If this number is odd, then we, with equal probability, 1/2 probability, find ourselves in a plus domain or a minus domain. Or in other words, there will be an unpaired kink, which can be a soliton or anti-soliton. And so I have to average over these possibilities. Okay, so this is the charge averaging step in the calculation. What about averaging over velocities and positions? Well, I still have to compute this number. And the idea is that the probability that a given pair intersects this segment from, let's say, from the left is given by this number, because it must come from an interval of length v times t. Otherwise, it will not arrive before time t at position x. Okay. Basically, it comes from the light must come from the light cone of this point, the past light cone. And because of translational invariance, I just divide this v times t over by the system size, because they are uniformly distributed in space. Okay? Now, the probability of a configuration with n plus right and n minus left crossings is just given by this expression. So this is a Poisson process. Basically, they are independent events. So this is the formula that you get. Here, this q is just given by this integral. Okay, and then the final result is obtained by simply summing over the possibilities. So summing over n plus and n minus these numbers that give the number of intersections. So each configuration has a probability given here, and as we discussed, if the number of crossings is even, then we have 1. If it's odd, then we have this combination, which is just cosine 2 pi alpha over beta. And it's trivial to do the sum, and we arrive at this result. Okay? So let me analyze the result. So this is an exponential decay, but not to 0 in general, but to an operator-dependent constant. So what I mean by that is that the result depends on alpha. And actually, it follows from this purely respective S matrix again, the asymptotic value, because if you think about it, after a long time, you can think that if you randomly pick a domain, with 1/2 probability, you find a 0 domain. With 1/4 probability, you find a plus domain, and with 1/4 probability, a minus domain. And then you just add these possibilities, and you end up with this asymptotic cosine square. Okay. Now the decay rate is very physical because this is just the collision time, because it is given by the ratio of the mean interparticle spacing, and which is 1 over rho, and the average velocity, which is given by this integral. Okay. If we expand it to first order, we recover the form factor calculation. But now we can decide what happens. So it's not a decay to 0 with a different rate, but it seems to be a decay to a constant with the same rate, because it's just the collision time. An interesting point is that you might remember that for this vertex operator, the form factor calculation actually gave a full result, not just an expansion. But this is a very simple case in my method, because this is just the Ising model in some sense. The reason why I say that is that e to I beta half times phi, which is my operator, in this case takes just plus or minus 1, so just two values. So basically the plus and minus domains, which I used to call plus and minus, are identified in this case, which means that now I don't even have to worry about the charges of the kinks. It's basically equivalent to an Ising model calculation, where there are domain in the ferromagnetic Ising model, when there are domain walls, and if a domain wall passes, it just flips the magnetization from plus to minus, and then from minus to plus. So it's almost trivial in this method to get this exponential decay. It has been obtained in other works before for the Ising model. And it's very interesting because it suggests that all the machinery, the exact S matrix, the form factors, the conserved charges that the paper used to construct the asymptotic steady state through the quench action method, these are do not seem to be really necessary to arrive at this result. So this is this is a leading order semiclassical calculation, but also in the form factor calculation was a leading order low density calculation. This is why they must agree actually. Okay, so now let's now go beyond these results, and let's look at general dynamic two-point functions and the time evolution of two-point functions. First, as a warm-up, we can look at this Ising case, so when alpha is beta half, and then we just have to count the number of configurations where only one member of a pair crosses this segment. So the operators are inserted here and here, because only these configurations do something non-trivial. They flip the magnetization between of the 2 points. Okay? And this has been done also in the paper by Evangelisti. The result is here. So somehow these three configurations translate into three terms, the product of three exponentials. Okay, I don't need to assume that I start with soliton anti-soliton pairs. I can even have soliton pairs for this in this Ising case. And Evangelisti derived this for the Ising chain actually, but the result is exactly the same. You just have to replace the you just have to take a trivial continuum limit of the lattice result. So it seems that, which is not obvious in general, that in the semiclassical regime, the scaling limit and the semiclassical limit, they commute somehow, which is not that surprising, I think, because the method works for really small quenches. So small quenches won't excite very energetic states of the chain, so the scaling limit can apply, can be true. Also for non-equilibrium processes. Okay. And then we were able to compute these 2-point functions for generic alpha. So the 2-point function of e to I alpha phi and e to minus I alpha phi. And then the trick was to consider all different kinds of configurations. The details are not very important here. I just want to show you that some horrible expression can be obtained. But the steps are very similar to this simple 1-point function calculation. So you need to sum up these series over probabilities, and then you get this. There are many q quantities here, which are defined through these integrals as before. Okay. So it's more instructive to look at some physical situations or limits of this expression. For example, we can look at the autocorrelation function. So the two operators are inserted at the same position in space, but at different times. So we have two time variables, t and t prime. And if t is at 0, and we plot it as a function of t prime, then we just get back this exponentially decaying result. But as soon as t, the smaller time, is not exactly 0, you can even see it from these plots, I think, that instead of an exponential, we have a much slower decay. And if you analyze the formula, you find that there is this Bessel function here that appeared there. And if you expand it for large time separation, then you get this diffusive behavior, this 1 over square root of t. And in finite temperature semiclassical calculation in the sine-Gordon model, similar diffusive behavior was found by Sajdev. So it's not very surprising. Something which is a bit, I find it a bit interesting, maybe it's trivial, that if I put alpha equals to beta half, which is this Ising case, then we always get this exponential result, and it does not depend on the time after the quench, only the time difference. So somehow this correlation function thermalizes immediately, and you can think that, okay, it's an artifact of this semiclassical approximation, but this was a similar behavior was observed in one of my previous works. We looked at the Tong-Girardeau gas, so the infinitely repulsive Bose gas, and there the result was analytically exact, and we also found that the autocorrelation function thermalizes or relaxes to its asymptotic value right away. So maybe it follows from the fact that these systems can be mapped to free fermions in a way. I mean, the sine-Gordon cannot for generic beta, but somehow this alpha equals beta half, as I said, is similar to an Ising problem. And also the Tong-Girardeau gas can be mapped to free fermions.
Can you do semiclassical also for 2-point correlation, two different operators?
What do you mean by two?
Alpha phi exponential gamma phi.
I think, so are these, I guess, I want to say that aren't these zero identical, but they are not, in infinite volume they are not, right? I think yes. I don't see any reason why, yeah.
So, I mean, in this book, it should be also interesting to look at not only correlations but also response function, and then check.
Yes, I was.
If the system thermalizes in this respect.
Yeah, like fluctuation, dissipation relations. Yes.
Why you call it diffusive behavior? Is there some kind of stochastic equation behind that?
No, it's just I just said this word because of this 1 over square root of t, but.
So there is no it equation which governs the equation?
No, there's nothing at this point, at least. There's nothing behind. Just that it has this strange 1 over square root of t.
Yeah, but maybe in your own time limit you become sort of random walker. Yeah, exactly.
Yeah, in some sense, yes, actually.
In this sense, it should be a sort of.
So because of this fully reflected gas mate, mass matrix, these domains somehow just do
You
like
have a
this,
representation
like a
of-
random walk or something.
So you have a representation of this correlation function in terms of Brownian motion or random walks? So do you have? No? Or
Say it again, sir.
do you have a representation of this correlation function or behaviors of kings or whatever in terms of random walks or Brownian motion?
Not yet, but I can easily imagine that it can be done.
Because at the end of the
Based on
day,
the-
when you have these n plus, now, I mean, in the other case, you have these n plus and n minuses, you can imagine these objects as being the number of steps taken to the left and to the right by random walk.
Yes, it's like a random
The
walk.
underlying statistics is always the same.
Yeah, so then I had another question which also related to the underlying statistics. How you define the probability measures that you use to compute everything?
So you're asking probably about this f of v,
Oh, you said some point that the
like this
statistics
probably.
is Poissonian. You have a Poisson
Ah.
somewhere. Why? Where does it come from?
No, that just comes from, that's somehow,
It's just a
but
chart.
these are independent events somehow.
Events.
So you can also do-
Talk about events. You have a probability measure or probability spread.
You- Yes, but I think it's quite straightforward at that point because so you know that the positions are drawn from a uniform distribution, the velocities are drawn from this distribution, and the charges are again like with 1/2 probability they are distributed, and then just by simple counting, I think you can yeah. So
It is an assumption.
Yeah, you start with quantum mechanics. You have, and then you go back to Poisson. You end up with Poisson processes at some point.
But I think basically in this
Sorry.
classical approach, you really make your problem classical.
yes. So this is
Meaning
just
that there is a
yeah.
sort of
exactly.
particles shooting, and that's it. You know, it's
Yeah, so
basically
it's-
classical.
So it's the input of the distribution.
Yes.
Yes, exactly. So it's just at this level, it's just an exercise in classical in geometry of straight lines or something like that, like or probability. Okay, but I will in a few minutes I will show you how to dress up this method by quantum mechanics or even more quantum mechanics. Okay, so where was I? Okay, here. So another case that I can look at is the equal time correlation function. This is the expression. This is what happens. It starts from here, and then eventually it takes this exponentially decaying form, and the correlation length in this exponentially is governed by the mean interparticle spacing. That's the only length scale basically that is relevant, and one can check that if you take the 2 points very far from each other, then the cluster decomposition principle holds at all times. So we get back the product of the two one-point functions. Okay. And then the last thing I want to show within this leading order semiclassical method is, of course, we can derive the asymptotic correlation functions for general 2-point functions. It has this form. And one thing that might be interesting is that if you assume for this f of v this power law behavior at zero velocity with some power k, then this will govern the approach to this asymptotic value of the 2-point function. So it will be a power law with a similar if it's k, it's k plus 1 power. Okay. So now let me add a few words about going beyond this semiclassical approximation. So as I try to emphasize, both this constant expectation value and both the diffusive, what I call diffusive dynamical correlations are clearly consequences of this very special S matrix and this very rigid structure of the domains. In particular, the entanglement entropy will not grow linearly in this approximation. And we know that it's quite general that after global quench in a translation invariant system, the entropy grows linearly, although wait for the talk of Pasquale tomorrow. Okay. So now, what can we say about this? So clearly, the true transmission amplitude is not zero, as Giuseppe said. It depends on the velocity in reality. So let's suppose that it's linear in velocity. Then clearly, after many collisions, we will see the effect of this transmission. So this is just a very basic estimate. If the collision rate is 1/tau, as I said, then after this time, when I raised this to the square to give the probability, these domains will change color. By this I mean that they will break this structure, and the sequence will change eventually. And this is quite interesting because it means that what we've seen so far is a pre-relaxed state somehow, pre-thermal. I don't call it pre-thermalized because it's not a thermal state, because this time scale can be very big if the quench is very small. But eventually, the system is expected to cross over to another asymptotic state. Okay. So we should put the S matrix somehow in this calculation. So and at the moment, what we would, or so far what we've done is to put it numerically, not analytically. Obviously, you can create these straight lines on a computer and compute everything. So one way is to do it through a classical Monte Carlo, which means that at each collision, we decide whether there's a transmission or there's a reflection based on the S matrix. The exact S matrix of the sine-Gordon model is known, so we can just take the S matrix and do it. So this is already much more than what we've done before, but still interference effects will not show up. And
indeed, I mean, you kill the interference.
Yes, exactly. I kill the interference in this way, but already it's a big improvement, I think, because all these very special constraints will be broken. But also another way to do it is to put the spin degrees of freedom, let's say, or the topological charge, consider it as a spin chain, and then you can follow the time evolution of that spin chain by some matrix product state-based method like TBD or DMRG or something like that. And then this truly follows the superposition of these internal degrees of freedom. So we put this TBD code as well as this Monte Carlo on top of this ensemble of classical straight lines. So you can call it a semi-classical method. And these are preliminary results that I'm showing now. So I mentioned the entropy, which used to do this. So this is the naive semi-classical result. Clearly, it must approach log 2/2 because with 1/2 probability, so if I cut my system in half, with 1/2 probability I cut a pair or I don't cut a pair. If I don't cut a pair, the entanglement is 0. If I cut, then I have log 2. So this is the result. And actually, this can be computed. This is a simple exponential function. It can be computed very easily. And this is what happens if we put in the S matrix. So this was the old result. So this is this, and then we see that after, so there might be a plateau, I don't know here, but eventually it starts to grow linearly as it should. These different curves are for different bond dimensions in the MPS code, so it doesn't need to bother you. It's a linear function only for a very small average velocity. And let's see what happens with this 1-point function. You remember that it decayed exponentially to a constant. So this is a log linear scale, so it decays to this constant. But then at some point, as we said, because of the possibility of transmission, it will decay further to 0. So this is what we see. This is what we expected, and this is indeed what we see. And also the 2-point function can be investigated. This is the different lines are for different times for the 2-point function. So we start from somewhere, and we approach this dashed line, which is actually the thermal result within the semiclassical approximation. So it's not, at the moment, it's not completely clear to me why this is thermal. One can say that the semiclassical approach is still not the full story, so it still breaks integrability in some way, some hidden way. So this is why, in the end, we find thermal results. Or maybe this correlation function is not sensitive to being in a thermal or in a GG. That I don't know. Okay, so yes.
Marton, do you have also results for the 2-time correlation function?
Yes, we have, but I don't have them here. Yes. Okay, so let me summarize. First, I showed you analytical approximations for both for 1-point and 2-point functions for small quenches using this intuitive semiclassical method. So we recovered these really cutting-edge, very hard form factor calculations. We reproduced the results of that calculation, but we were able to extend them by computing 2-point functions, for example. This is just a speculation that these results can be valid even in the attractive regime of the sine-Gordon model, where we also have breathers, because breathers, the S matrix. So the breathers have topological charge 0, so they will act as spectators in this whole picture. At least for not very deep in the attractive regime, it might be true. And then I reported some preliminary results with this upgraded version of the method, this semi-classical approach, where we try to follow this internal degrees of freedom in a better way, taking into account quantum mechanics at another level, basically. And I mentioned this, that the method in principle does not rely on integrability. Of course, in a non-integrable system, one has to come up with a reasonable 2-particle S matrix. In this case, it was known exactly, of course, in the sine-Gordon model. So this method is quite generalized. I think it can be used in other models. So it can be used in spin chains, lattice systems, or in continuum systems or field theories like here. Okay, thank you very much for your attention.
Questions?
So coming back to the initial state that you have. So can you apply or try to think to apply the semiclassic approach also if you have an initial state which I mean, for example, has some inhomogeneous profile in the field phi?
That's not a problem, I think. I mean, analytically, probably it is, but doing this numerics, you can you just distort your initial straight line configuration.
In that case, you will have some behavior with beta, depending whether you are in the gapless phase. I mean, when the cosine is irrelevant, or when it is
yeah. So the method only works for it's important that we have a gap system, because otherwise, no matter how small the quench is, you can create many particles with zero mass. So it's important that it's a gap system. You create just a few particles, low density, and then this picture, to some extent, applies. But in homogeneous initial states or finite systems or whatever, these are not these don't pose any difficulty.
So you mentioned before that maybe you are describing some pre-relaxation regime. So my question is, have you any idea about the time scale of this?
So there was this very naive estimate for which was like C over 1 over v square, where v is times the collision rate, collision time, sorry. So tau over v square was the naive
So is it related to how much far is the model from being non-interacting or not?
So,
So because we think that maybe your approach is exact in the non-interacting limit. So what I'm thinking, maybe if this time scale is related to the distance between the non-interacting.
yeah, in some sense, but
Maybe, I don't know.
so what we work with here is this velocity distribution, and we have the S matrix. So somehow from that we can define the distance from a free model, and we can also try to measure. We haven't done it yet in these plots. Somehow define the length of this plateau, if there is a plateau, and when it starts to cross over, and so on. But we haven't done it yet.
Other questions? I have a few myself. I mean, I think the last remark, in your approach, essentially everything is -1. So either is -1 or, I don't know, you can, so I want to say in semi-classical, any cut becomes gray. I mean, it's only the same, nothing.
Yes, you mean the first part of the talk when?
No, but also when it doesn't rely on integrability, yeah, but it doesn't rely also on particular matrix because it's only -1, nothing else.
Yeah, in the first part of the talk.
Sure, but I mean,
Yes.
and if you start non-integrable case, if you start into structure, you break immediately all the entire picture. But then I think also semi-classical can be very, very misleading. What I mean is the paper of Evangelisti you quoted, the O3, I think you got a paradoxical result because you expect that the symmetry is restored or quenching. I mean, you have no other expectation, I would say. Nevertheless, the fact that you don't put any transition, because -1 is -1, it doesn't do anything to the system, leave it frozen.
Yeah. This is what happened here.
It does something, you get some, say, non-trivial formula as well, but nevertheless, they might be completely off the real dynamics. Do you agree or not?
Yes, this is what happened here as well, I think. So that this various operators did not decay to 0. It's something like that. That something is not restored, as you say. But then this is why we've been working on extending the method by putting the S matrix, and then we indeed see. So I expect that if we at some point if we do it for the O3 sigma model, probably we will find
So, I mean,
different result. I'm sure that we will find different
I
results.
think it's fair point to say that semi-guy is just the first brutal steps, but it's not any other.
Yes, but what is important to see, I think, on a practical level, that the first principle of calculation done by Fabian is really, really hard to do, and it was a 50-page paper, and this is what you can do and it's the same as this. So also in that case, you can also only go to the leading order.
But their assumption is that they were a low energy. So this is why they match with.
Yes, low density and low energy. So they also work in the same regime. They cannot. I think it's a pity that Fabian is not here yet, but apparently they cannot really go further at present, at least.
Okay. Other comments? If not, let's go take coffee.
So thank you.